Last video, I left you with a puzzle. The setup involves two sliding blocks in a perfectly idealized world where there's no friction and all collisions are perfectly elastic, meaning no energy is lost. One block is sent towards another smaller one, which starts off stationary, and there's a wall behind it, so that the smaller block bounces back and forth until it redirects the big block's momentum enough to fully turn around away from the wall. If that first block has a mass which is a power of 100 times the mass of the second, for example, 1,000,000 times as much, an insanely surprising fact popped out. The total number of collisions, including those between the second mass and the wall, has the same starting digits as pi. In this example, that's 3,141 collisions. If that first block was 1,000,000,000,000 times the mass, it would be 3,141,592 collisions before this happens, almost all of which happen in one huge, unrealistic burst. And speaking of unexpectedly big bursts, in the short time since that video went out, lots of people have been sharing solutions and attempts and simulations, which is awesome. So why does this happen? Why should pi show up in such an unexpected place and in such an unexpected manner? Foremost, this is a lesson about using phase space, also commonly called configuration space, to solve problems. So rest assured that you're not just learning about some esoteric algorithm for pi. This tactic here is core to many other fields, and it's a useful tool to keep in your belt. To start, when one block hits another, how do you figure out the velocity of each one after the collision? The key is to use the conservation of energy together with the conservation of momentum. Let's go ahead and call their masses m1 and m2, and their velocities v1 and v2, which will be the variables changing throughout the process. At any given point, the total kinetic energy is 1/2 m1 times v1 squared plus 1/2 m2 times v2 squared. So even though v1 and v2 will be changing as the blocks get bumped around, the value of this expression must remain constant. The total momentum of the two blocks is m1 times v1 plus m2 times v2. This also has to remain constant when the blocks hit each other, but it can change as the second block bounces off the wall. In reality, the second block would transfer its momentum to the wall during this collision, and again, we're being idealistic, say thinking of that wall as having infinite mass, so such a momentum transfer won't actually move the wall. So here we have two equations and two unknowns. To put these to use, try drawing a picture to represent equations. You might start by focusing on the energy equation. Since v1 and v2 are changing, maybe you think to represent the equation on a coordinate plane where x is equal to v1 and y is equal to v2. So individual points on this plane encode the pair of velocities of our block. In that case, the energy equation represents an ellipse, where each point of this ellipse gives you a pair of velocities, all of which correspond to the same total kinetic energy. In fact, let's actually change our coordinates a little bit to make this into a perfect circle, since we know that we're on a hunt for pi. Instead of having the x-coordinate represent v1, let it be the square root of m1 times v1, which for this example shown stretches the figure in the x direction by the square root of 10. Likewise, have the y-coordinate represent square root of m2 times v2. That way, when you look at the conservation of energy equation, what it's saying is 1/2 x squared plus y squared equals some constant, which is the equation for a circle. Which specific circle depends on the total energy, but that actually doesn't matter for our problem. At the beginning, when the first block is sliding to the left and the second one is stationary, we're at the leftmost point on the circle, right? Where the x-coordinate is negative and the y-coordinate is 0. What about right after the collision? How do we know what happens? Conservation of energy tells us that we must jump to some other point of the circle, but which one? Well, use the conservation of momentum. This tells us that before and after the collision, the value of m1 times v1 plus m2 times v2 must stay constant. In our rescaled coordinates, that looks like saying square root of m1 times x plus square root of m2 times y equals some constant. And that's the equation for a line, specifically a line with a slope of negative square root of m1 over m2. You might ask which specific line, and that depends on what the constant momentum is. But we know that it must pass through our first point, and that locks us into one choice. So just to be clear about what all this is saying, all other pairs of velocities which would give the same momentum live on this line, in just the same way that all other pairs of velocities that give the same energy live on this circle. So notice, this gives us one and only one other point that we could jump to. And it should make sense that it's something where the x-coordinate gets a little less negative, and the y-coordinate becomes negative, since that corresponds to the big block slowing down a little, while the little block zooms off towards the wall. From here, it's quite fun to see how things play out. When the second block bounces off the wall, its speed stays the same, but it goes from negative to positive, right? So in this diagram, that corresponds to reflecting about the x-axis, since the y-coordinate gets multiplied by -1. Then, once more, the next collision corresponds to a jump along a line with slope -square root of m1 over m2, since staying on such a line is what conservation of momentum looks like in this diagram. And from here, you can fill in the rest for how the block collisions correspond to hopping around the circle in our picture, where we keep going like this until the velocity of that smaller block is both positive and smaller than the velocity of the big one, meaning they'll never touch again. That corresponds to this triangular region in the upper right of the diagram, so in our process, we keep bouncing until we land in that region. What we've drawn here is called a phase diagram, which is a simple but powerful idea in math, where you encode the state of some system, in this case the velocities of our sliding blocks, as a single point in some abstract space. What's powerful here is that it turns questions about dynamics into questions about geometry. In this case, the dynamical idea of all possible pairs of velocities that conserve energy corresponds to the geometric idea of a circle. And counting the total number of collisions turns into counting the total number of hops along these lines, alternating between vertical and diagonal. But our question remains, why is it that when that mass ratio is a power of 100, the total number of steps shows the digits of pi? Well, if you stare at this picture, maybe, just maybe, you'd notice that all of the arc lengths between the points on this circle seem to be about the same. It's not immediately obvious that this should be true, but if it is, it means that computing the value of one such arc length should be enough to figure out how many total collisions it takes to get us into that end zone. The key here is to use the ever-helpful inscribed angle theorem, which says that whenever you're forming an angle using 3 points on a circle, P1, P2, and P3, like this, it will be exactly half of the angle formed by P1, the circle's center, and P3. P2 can be anywhere on the circle, anywhere except between P1 and P3, and this lovely little fact will be true. So now look back at our phase space, and focus specifically on 3 points, like these. Remember, that first vertical hop corresponds to the second block bouncing off the wall, and that second hop, along a slope of -square root of m1 over m2, corresponds to a momentum-conserving block collision. Let's call the angle between this momentum line and the vertical line theta. And now maybe you see it, using the inscribed angle theorem, this arc length between those two bottom points, measured in radians, will be 2 theta. And importantly, since the momentum line has the same slope for all of those jumps from the top of the circle to the bottom, the same reasoning means that all of these arc lengths must also be 2 theta. So for each hop, if we drop down a new arc, like so, then after each collision, we cover another 2 theta radians of the circle. We stop once we're in that end zone on the right, which remember corresponds to both blocks moving to the right with the smaller one going slower. But you can also think of this as stopping at the point when adding one more arc of 2 theta would overlap with the previous one. In other words, how many times do you have to add 2 theta to itself before it covers more than the whole circle, more than 2 pi radians? The answer to this will be the same as the number of collisions between our blocks. Or, to say the same thing more compactly, what's the largest integer multiple of theta that doesn't surpass pi? For example, if theta was 0.01 radians, then multiplying it by as much as 314 would keep you below pi, but multiplying by 315 would bring you over that value. So the answer would be 314, meaning if our mass ratio was one such that the angle theta in our diagram was 0.01, then the blocks would collide 314 times. So now you know what we need to do. Let's go ahead and actually compute the value theta, say when the mass ratio is 100 to 1. Remember, this rise over run slope of that constant momentum line was the -square root of m1 over m2, which in this example is -10. That would mean that the tangent of this angle theta, opposite over adjacent, is the run over the negative rise, so to speak, which is 1 divided by 10 in this example. So theta is going to be the arctan of 1/10. Speaking more generally, it'll be the inverse tangent of the square root of the small mass over the square root of the big mass. If you go ahead and plug these into a calculator, what you'd notice is that the inverse tangent of such a small value is actually quite close to the value itself.